To the final session of BlinkOn 11. So we have 11 more speakers today, which is great. So as always, so we have one important rule. So I asked all the speakers to insert one talking point that will get a storm of applause. So when you find that point, please give the speaker a storm of applause. Is that okay? Okay, so let's practice number 3. So in yesterday's keynote, Ian highlighted crbug.com reached 1 million. So this is great. But do you know what is crbug.com 1 million one? Do you have any idea? Okay, so I can show you this one. Test expectation will look messy when bug numbers don't have the same amount of digits. So we are talking about this problem, right? And this bug is available, so please take it and fix. All right, so I want to call the first speaker to the stage, Brian.
On? Okay, so it's me. Being able to render and share your text isn't controversial. It's kind of the web's thing. And the math element is about the standard markup that lets you do that for all the maths. This is important because math is an important part of many writing systems, any writing system really, and it has its own rules that are non-trivial. For one brief shining instant, we had 4 implementations. And then I'll say that not all of them were especially good, to be honest. So when Blink split from WebKit, the math element was removed. And about this same time, the Extensible Web Manifesto came about. This was not great for MathML because the Extensible Web Manifesto asks us to treat existing features and new features differently. So the question is, which one is MathML? It has this amazing ecosystem outside of browsers and lots of existing content. It's very requested, and it's in 2 of the 3 browser engines. It's in the HTML standard. But today, if you look at some MathML in your Chromium browser, it looks like this, but it should look like this, which is, of course, unacceptable. So we do things to turn it into images and SVGs and use JavaScript libraries. And this is weird stuff to think about for text, right? This is what the web does. So Igalia and some sponsors worked with the MathML Refresh community group on MathML core. And its goal is to find the minimum subset of what is necessary, and then to resolve all these weird things from the past about its coevolutionary past, say very specifically how it fits into the platform. Things like basic modern expectations, you would expect all of these things to work, but they did not. We wanted to define it and apply modern testable rigors to it. So this is our implementation. You can see it's scoring 98.63% of about 2,000 tests. Gecko and WebKit doing slightly less well, but they have honestly come up, and this is what that level of interoperability looks like, so it's really quite good. So we're establishing good foundations from which we can build up new things or drill down and find things like how we discuss stretchy characters, what is the magic, and how we integrate with all these new ideas like Shadow DOM to build up really cool things. So we filed an intent to implement. We have a tag review, and preliminary patches have already begun landing. That's it. Thank you.
Thank you very much. The
35
next
slides.
Yeah, the next speaker is Hyungwook.
Hi, I am Hyungwook Lee, working at Naver company. We released a web browser which is based on Chromium 3 years ago. It's a baby browser. We support 3 desktop platforms and 2 mobile platforms. Today, I want to introduce the SRA cache So many websites use popular JS and CSS framework. As we know, React and Angular.js. It will be good if we can share same content between websites, but we cannot share same content in HTTP caching because HTTP cache use URL as a key, and frameworks URL is not same each other. To achieve this goal, we need to find a way to guarantee same content. So by URL, it looks difficult. So basic idea comes from W3C sub-resource integrity spec. We can see the integrity value on script tag in example. So sub-resource integrity spec provides a method to protect website delivery using hash value. So SRL cache use hash value for key and guarantee same content by hash value. So same content means same integrity value. And advantage of SRL cache is easy to use. We just needed hash value of content. SRL cache is not same as HTTP cache. It's more than HTTP cache. In case of JS, we can add the AOT feature. So there is no loading and no compile time. We can execute directly. In case of CSS, we can add pass the CSS feature. So there is no loading and no passing time. This advantage of SRL cache is difficult to use. As we know, the hash value is not human readable, so managing hash value is not easy. Yeah, we already shipped this feature. You can enable it in Rail flags and see how it works in DevTools. Thank you.
Thank you very much. The next speaker is Robert.
Hi, I'm Rob Flack. I am on the animations team, and I'm going to talk to you about scrolling to animations, or time travel through the animation timeline. So normally, animations progress forward through time. The animation on the left is just repeating. The animation on the right never actually finishes an iteration. We're just scrolling forward and then backwards through the animation timeline. So people are doing this all over on the web. You might have seen this on some major product launches. They don't have access to scroll timeline. They're doing it with scroll events and updating the main page. So you might notice that those animations were a little janky. And that is because of that reason. They have to run script to update the page. The page then has to render a new mainframe. And Chrome is trying to optimize scrolling and saying, like, hey, we know how to scroll. So even if the main thread has produced a new frame, we're just going to go scroll that previous frame you had without waiting for the new mainframe. So the idea is if we can make scroll length animations declarative, we can do them on the compositor. And that's what you were seeing previously through this mechanism, scroll timeline, which is a new type of animation timeline similar to the document timeline. But the time value is determined not by wall clock time, but the progress through a scroller given a start and end position. We did an origin trial of this in combination with animation worklet with AMP. And from that process, we have moved the spec out of incubation into the CSS working group. And we're working towards a first public working draft. We identified some issues. I'm going to show you one of the interesting ones. So there was a bit of an ergonomic challenge. Scroll timeline had a start and end offset, and you would calculate these based on when you want something to happen, like your lightning bolt to fly into the screen. And then imagine something changes on your page, that green box has grown, and now the start and end offsets are no longer correct. They should actually be lower. And so the developer would have to detect anything that could cause those offsets to become invalid. So we updated the API to have element-based targeting so that you can say when an element progresses through the scroll port, and that makes it much easier to use. We have the basic JavaScript API implemented. This is all behind a flag. A polyfill of this and integration with animation worklet. We're just working on integrating with regular animations and with web animations as well. it's going to be a close collaboration. It has been a close collaboration with Microsoft, and we have a polyfill that you can try today. So this will let you play with the API. You simply just import this library, and then you can create a scroll timeline, plug it into your animation. This will be main thread driven, of course. As a bonus, if you create an animation where the thing you are animating is, how do I play a video? If you plug your scroll timeline into a progress that drives a paint worklet animation, you can then animate something like Lottie from your scroll, and this will all be on the compositor thread by next BlinkOn, I promise.
Done. Great. The next speaker is Mythri.
I am Mythri. I work in V8 mobile team in London. Today I'm here to talk about the middle tier compiler for V8. Currently, V8 has a two-tier pipeline. We initially start off with ignition, which executes bytecode. And when V8 finds that some functions are hot, it recompiles them using turbofan, which is the optimizing compiler. When we look at the data from our real-world benchmarks, we see that we only spend 10 to 30% of the time in the optimized code, which is not very high. So we started looking into a potential middle-tier compiler. This plot here shows the potential amount of code that could be optimized using a middle-tier compiler, starting from a very aggressive tiering up strategy to a very late tiering up strategy. If we leave out the extremes, we still have about 30 to 40% of the time which we could optimize. So then the next question is, what kind of middle-tier compiler we are looking at? So to answer this question, we looked at 3 different points in the solution space, starting with Sparkplug, which is like a very fast baseline compiler, which just generates the machine code instead of bytecode, doesn't do many optimizations. Then TurboProp, which is like a cut-down version of turbofan, which does not do as many optimizations as turbofan. And the last is early turbofan, that is like using turbofan itself as a middle-tier compiler that is optimizing sooner. So when we ran experiments with each of these things and looked at the JavaScript execution time, Sparkplug did improve a bit, but when we consider the additional compile time we need to, additional compile time, that is not like a really worth middle tier compiler because the overall improvement is not very high. But both for turboprop and early turbofan, the JavaScript execution time improvements are reasonably high. And when we look at the compile time, turbofan doesn't scale that well. So turboprop is the chosen middle tier compiler. What exactly is turboprop? This is the turbofan pipeline, which has like an extensive set of optimizations. With turboprop, we want to drop all the optional optimization phases and also replace some of the non-optional ones with simpler variants, which use less compute time. And we want to finally get to that pipeline, which is like a bare bones turbofan. We started working on turboprop starting this quarter, so we are not quite there yet. But as we simplify the pipeline, we are actually tracking both the compile time and the JavaScript time. So we are already seeing some improvements in the compile time, which is shown in the top graph. But the important thing is the JavaScript execution time is not regressing. We still see about 9 to 10% improvement. So hopefully by next BlinkOn, we should have the turboprop ready and share more detailed results with you. Thank you.
Thank you very much. The next speaker is Lorne.
So my name's Lorne. I work for Microsoft on the DevTools. And today I'm going to talk to you about a new feature we're adding called 3D views for the DevTools. So first, this is the tool that we all know and love for debugging the DOM, right? You understand the HTML layout. It's good for understanding the trace styles that are applied to elements. It's good for adding, DOM mutation breakpoints, but it's not great for understanding the render order of elements. So is there something we can do in that regard? So we took inspiration from a product that Firefox put out a while back called Tilt, and used a product called Babylon.js and built this 3D view here. And this is showing the DOM nesting of your page. We actually render the texture on top and everything. And this can be useful for debugging some cases, but not necessarily the render order of the elements. So what can we do to further that? So this is an example. So we need to understand render order, we need to understand z-index and stacking context. So this is a very simple example from the MDM website that shows 6 divs. And each one of these divs creates what's called a stacking context, which is a node. And these nodes are chained together into a tree. And they determine the order that your elements actually get rendered onto the screen. So the interesting thing here is that div 1 is actually rendered on the top, and it's got a z-index of 5. Div 4 here has a z-index of 6, yet it's rendered below. And this is pretty easy to understand why here. It's relative to its parent. Its parent div here is div 3, which has a z-index that's less than div 1's, and so it gets rendered under. So you can put any z-index that you wanted on div 4, and it's not going to render on top. So can we make a 3D view to make this more apparent, right? Because this is not clear if you're looking at the page and the page is complex. The elements tool does not help with that. So we think we can. Here's the page rotated perpendicular to the viewer. You're looking up that z-axis at it. And you can see each of these orange bounding boxes with the tags next to them represent a stacking context. And so it's very clear which order these are rendered in. You can click on one of those and it'll actually select that element in the elements tool. So you got correlation between the two tools. We think this will help a lot with debugging render problems. But how well does this scale to a larger, more complex page? So we took this Twitter post here. I've got a video, and you can see it really balloons out. It can be a bit hard to deal with, and so we've added some filters. There's a filter that'll actually remove all elements that are not stacking context, and it'll collapse down. And then you can click on any of those elements that are stacking context, zoom in on them. It'll highlight in the elements page, and we think this is super powerful. We're actually doing some user tests this week at Microsoft, and the feedback has been excellent. And I'll mention this is already in Microsoft Edge behind an experiment, but this is coming to Chromium. We've got a CL up against the DevTools front end right now for this. And we are adding a couple more features. So we're going to highlight the recs on the screen so that you've got correlation between what you're seeing on the screen, this product, and the elements tool. And then finally, there's already a layers tool you might know about. We're putting a third mode into the 3D views that will subsume this. So that's the work we've done.
Thank you very much, Lorne. The next speaker is Lorne.
Yeah, so I got another talk. Okay, so this is where I spent a lot of my time actually, is on building a more inclusive set of the dev tools. And what do we mean by that? Well, we're looking to enable web developers with a broad set of abilities to do their best work through inclusive features. And so our current in-market browser, Edge, built on Edge HTML, not the new Chromium one, has a set of developer tools with a bunch of assistive technologies that our customers have come to expect. And so we're working to take the best of those features forward into the Chromium dev tools. Specifically, we're investing heavily in localization and accessibility here. So localization, this is about enabling web developers to do choose the language of their choice. This is actually the dev tools rendered in Japanese. And you can imagine, I don't speak Japanese or read Japanese. This is like completely incomprehensible. I wouldn't be able to use it. This is the scenario we want to light up for individuals that don't speak English well or don't speak English at all. So what work did we do here? We made sure all the English strings are ICU compliant and are looked up at runtime. So there's an ID now. We look up the translated string and can present that. There's descriptions for all of the strings that we handed off to your loc pipeline that can actually give you back quality translations. CDP, which is the protocol that we talk to the browser over from the front end. There were some areas there. We did some work to make sure that's all completely localizable. And then the Lighthouse team actually stepped up and did some work here so that the audits tool, it's got a bundled version of Lighthouse. That's all localized. So these reports will be returned in the appropriate language. So for launch, at least with Microsoft Edge, we've got 10 languages plus English. And we also have an option. So if you're used to English and you want to just fall back to English, there's a setting that you can check if you want to use your browser in another language with the dev tools in English. All of this is being contributed to Chromium, so you can look forward to that coming. Second, accessibility. So one of our PMs, Chris Heildman, put out a tweet asking for users with disabilities to try out the accessibility features that we've been adding. This particular user is blind, and you can see kind of the strong negative sentiment here towards the current experience in the dev tools, right? So what can we do to improve that? So we've spent a lot of time over the last 6 to 9 months with hundreds of changes to make the product a lot more accessible. We're moving towards WCAG 2.0, which is the Web Content Accessibility Guidelines. And we did a lot of work around keyboard navigation. So anything that you can do with a mouse, you should be able to do with a keyboard. And this includes like focus indicators on the screen, right? And making sure all your tab orders are correct, making sure the keys can expand and collapse elements, et cetera. Second, screen reader support, very important. This is making sure all the elements on the page in the tools have ARIA labels on them so that the screen reader can provide enough context back to the user. So that's coming. Finally, this is the response we got back from that same user, much more positive response. We think this is, awesome. And again, all of this stuff is being contributed to Chromium, so it'll benefit you guys as well. It'll benefit Chromium as well. So, thanks.
Thank you very much. The next speaker is Nicolas.
Hi, everyone. I'm here to talk to you about keeping track of embedder-owned services in Chromium, whether it be Google services or, in our case, Microsoft services. So you might be wondering why this matters. So sometimes enterprises will ask us what Google services exist in the product before you replace them in Microsoft Edge. They might want to know what services we've added. They might want to know which of ours are direct replacements for Google services. So we need a way to keep track of this. We also, in our case, want to make sure that our customers aren't getting their data sent to a company that isn't us, because that's not what they signed up for. So we need a way to kind of keep track of this stuff. So first tool we use is this awesome idea that Chromium engineers came up with called network traffic annotations, which many of you are probably familiar with. So the idea here is every network call that goes through the Chromium network stack is required to have a network traffic annotation. The cool thing here is that they specify a destination, which can be a website, it can be local, it can be whatever other. And in this case, they are actually able to specify a Google-owned service, which in our case, we'll use Microsoft-owned service. So another cool thing that the Chromium team came up with is the network traffic annotation auditor. So this thing is pretty cool. So this will scan through the entire source code, figure out what got built, and then have an inventory of all the annotations that exist in the product. And in the end, it'll spit out this summary file. And again, this is something that many of you are probably familiar with. But the idea here is this is the one place where we keep an inventory of all network calls that go through the Chromium network stack. And when we have our own version, the Edge version of this thing, we can diff the two files. And we can know immediately exactly what services we have that do not exist in Chromium and vice versa. And with a particular naming scheme, we can figure out which of our services are direct replacements of Google services. So this is great. So far, we have a great idea of what network calls exist in the product that go through the Chromium network stack. But we don't have the full picture yet. There are some cases that are not accounted for. For example, there may be component extensions, which are packaged with the product and will go through a regular network annotation, one that it doesn't say a Google or Microsoft-owned service. Additionally, there are some features, at least for us, that go through Windows OS APIs. And those will do their own networking at a layer that we can't see. So we don't actually know the full picture. So we have a detective tool that we call Source Scanner, which basically just runs regex over all the product. We filter out some files that we know don't actually make network connections, like the documentation folders and test folders. But the idea here is let's figure out which URLs look Microsofty or which URLs look Googly. And then we'll keep track of those in a CSV. This depends a little bit more on manual work and making sure that we maintain the truth in these files. But it is another great way for us to have an automated system that runs in our CQ to make sure that we don't accidentally introduce a new link that'll take you to the Google login page when we actually want it to go to the Microsoft login page. But this still isn't quite enough for what we want. So this will account for the component extension case, but it won't account for Windows OS APIs. So we have a runtime analysis tool. And so the idea here is let's figure out all the network calls that come out of the box Also run netlog, figure out which of those calls go over the Chrome network stack, and then figure out which, the difference between them basically. So which calls actually went through Windows OS APIs. And now we know what's going on in the product. So yay.
Thank you very much. The next speaker is Tarun.
Hey, I'm going to talk about the cost of JavaScript and how we can minimize that cost. I'll just use this. Yeah, so I don't know how many of you have been recently on a 3G connection, but if you try to load a web page, it takes like 30 seconds to load. And sometimes it's so flaky that it doesn't even work. Like in this case, the video load fails at some point. And that makes our users, in this case, a dinosaur, very unhappy. So how can we fix it? One way is to, well, let's go and disable the JavaScript. So we disable the JavaScript, we try to load the same web page. It works really fast, only 4 seconds. But a lot of features are broken. The interactive menu doesn't work, the video player doesn't work. So that's not a good solution, right? So so back to the whiteboard, what can we do? We cannot disable the JavaScript. So maybe we can take some intermediate step. We enable the JavaScript, but we don't block the render or the paint on the execution of the JavaScript. So at a high level, we are basically just inserting defer tags into the JavaScript, into the source code, even though the web developer wants to execute JavaScript synchronously. Not spec compliant, definitely. But how does this perform? Well, 6 seconds FTP, much better compared to 15 or 20 seconds, and everything works well. So nice trade-off. Page loads incrementally, and the loading of the content, like whatever you could get from HTML and CSS, is not blocked behind JavaScript. And once that loads, the defer JavaScript runs and restores the interactivity and the video player and everything else, which makes the user happy. So what did we find in our experiments? Pages contain a lot of JavaScript, like 95th percentile. A web page contains like about 65 script tags. And about 30 of them are like external files. So we are downloading 30 files and we are loading them and then we are executing them. And we saw about 25% reduction in the path start to FCP for users. So that's pretty good. So what's our obvious conclusion? Obvious conclusion is a lot of times JavaScript is not necessary in the rendering path. But well, how can we encourage the web developers to make more use of asynchronous JavaScript? That's it.
Thank you very much. The next speaker is Daniel.
Hi, my name's Dan Clark. I'm a dev on the Microsoft Edge team, and today I want to talk about CSS modules with regards to performance and memory wins. So Microsoft has this goal of improving the web component authoring experience. One of the ways we want to try and do this is by helping to drive a few different proposals for expanding the ECMAScript module system to include different additional content types. So currently we have JavaScript modules, and that's great. We would like to also have CSS and HTML modules, sort of completing the trifecta of web languages. JSON modules is another thing we're interested in. So we think these all have like pretty compelling benefits for developer ergonomics, but I'm going to ignore all that today and just talk about CSS modules and drill into some fun performance findings. So CSS modules are built on constructible style sheet API. That's this idea where I can instantiate a style sheet without having to go through like a style element or a link element. I can just have one by itself. With CSS modules, I can just pull one of these in right from a CSS file with the classic import syntax and stick that into an adopted style sheets array on my document or my shadow root. So we see this as replacing a couple contemporary ways for setting up styles in a custom element definition. Like today, I might, in my custom element constructor, in my shadow root, I might stick a style element in there with my styles, or equivalently like a link element. In the future, we're thinking a CSS module can be imported at the top level of the custom element definition, and then you can stick that style sheet in the shadow root adopted style sheets array. It turns out that these three different approaches have performance implications. If I have a whole ton of custom element instances on my page, the CSS module approach can be a lot faster. Why is this? We took some performance traces, and the key observation here is that for the style and link approaches, for every instance of the custom element on a page, that's another like DOM element that I have to stamp out, and then I have to run the insertion rules whenever, like for each instance of the custom element for the style or link. And if I have a whole bunch of custom elements, that adds up. Whereas with the CSS modules approach, I just have one style sheet that gets shared everywhere. For similar reasons, the memory impact of CSS modules is also different for basically the same reasons. I don't have the style and link elements that I have to stamp out everywhere. For those same test pages, the link element version came in at about 161 megs. Style element is better at like 140 megs or so usually, and CSS modules squeaks under at 134 megs. So for in the future, you'll be able to use CSS modules to build web components that are smaller and are faster, and we'll also have better web developer ergonomics, which is maybe a subject for a future talk. If you want to play with these demos yourselves, the link's here. If you don't want to go dig in the slides for this, just shoot me an email. Email's on the slide. I'll send these links up. Thanks.
Thank you very much. The next speaker is Kevin.
Hello, my name is Kevin Babbitt from the Microsoft Edge team, and I'm here to talk about making virtualized content accessible. So what is virtualized content? One example comes up when you're working with a large document in an online productivity suite, and you actually don't have the entire document loaded in the markup at the same time. Another example comes up when you're reading a website that has an infinite feed. In either case, you'll be reading and scrolling down, and you reach a point where the site sends a request to the server for more content, and then once it loads, you can continue reading. Now, this works great if you've got a keyboard and mouse, but what if you're working with a screen reader? My sample document here has a total of 8 links in it, so let's point a screen reader at it in a mode that lets us scan quickly through those links and see what happens.
Details for section 1, link. Details for section 2, link. Details for section 3, link. No next link.
We only found 3 of the 8 links. And the reason why is because the rest of them aren't actually in the document, right, in the DOM right now. They've been virtualized away. And the screen reader and we didn't scroll enough to get them to load. And the screen reader has no idea that it can actually do that. And so what if we gave it a hint? The ARIA virtual content proposal, which is currently in the explainer stage, lets us do that. And we're still working on the syntax and so on. But the basic idea here is to let screen readers know that if they scroll a certain element to its end, that more content will load. So let's take a look at how this works in a prototype.
Details for section 1, link. Details for section 2, link. Details for section 3, link. Demo page, loading additional content. Next 3 sections loaded. Details for section 4, link. Details for section 5, link. Details for section 6, link. Demo page, loading additional content. Next 2 sections loaded. Details for section 7, link. Details for section 8, link. No next link.
And that was the last link because we actually reached the end of the document. So once again, the explainer is called ARIA Virtual Content. The link is here. Please feel free to leave comments on it or send me feedback and questions. Thank you.
Thank you very much. The final speaker is Sanket.
Hi, everyone. My name is Sanket, and I'm a dev on the Microsoft Edge team. And today I want to talk about the work we've been doing to refresh the look of form controls in Chromium. Our goals with this work were to improve touchability, accessibility, and overall appearance of controls. And I'd like to share some examples of that. An example of our touch improvements can be seen with the time control. On the left is the experience we have in Chromium today. As you can see from the video, it's not an ideal experience for touch. You have to click on really small icons with your finger, and while your finger is over the control, it's hard to see what's underneath. On the right is the refreshed look of the time control, which uses a time selection pop-up to make it much easier to look through values and select the ones that you're interested in. In terms of accessibility, we've made improvements in a few different areas. Firstly, we've added support for the Windows high contrast themes to provide a better visual experience for users that are using the Windows accessibility color schemes. Secondly, we've made our controls more keyboard accessible. An example of that can be seen with the color control. On the left is again what we have in Chromium today. On Windows, it uses a Windows native color picker dialog that doesn't allow you with just a keyboard to select the colors that you see on the screen. The experience on Mac and Linux is similarly keyboard inaccessible. On the right is the refreshed look of the color picker that is cross-platform and completely keyboard accessible. You can use the tab keys to navigate through the parts of the color picker and then use the arrow keys to select the colors that you want. We also built on the work done by Rosin's team to add UIA support for our controls, and we also made our controls more ARIA compatible. This has helped gain an increased score on HTML5accessibility.com. Edge HTML-based Edge scored 100% on this benchmark. With these controls improvements, combined with all the other accessibility work that has happened via other teams, Chromium-based Edge will also get to 100%. Additionally, Chrome will also get to 100%. Lastly, we just wanted to give our controls a new and refreshed look. Several of these controls have looked the same for several years now, and we just wanted to align their appearance with today's design styles and give our users something that they can get excited about. Finally, before I close, I just wanted to say a big thank you to everyone at Google for helping us pursue this project, especially Chris, Kent, Mason, Wee, and Nicole. This has been a great collaboration between Microsoft and Google, and everyone at Microsoft that's been involved in this project has really enjoyed working with all of you. So thank you very much.
So thank you very much. So everything finished. We are on time. So thank you very much. So I'm so happy to see. So what? Yes. This is an expectation. So this is great. So I'm happy to see so many non-Google contributors to the writing sessions. So Inaria and Navier and Microsoft and individual contributors. So it's so amazing. So thank you very much for joining. So see you next time in London.